In this series of videos I'm designing a Z80 based computer system. So far in this series I've put together the basic video in-out circuits and I've started assembling the core CPU system. Now I've had a few people commenting saying that there are easier ways to build Z80 systems these days. Yes, I'm fully aware of that, and that is really the whole point of this series of videos. I'm trying to show what it was like to design and build Z80 systems before we had the current safety nets of large-scale devices. So these days you could use a CRT controller chip, you could use a DRAM controller chip, or you could just throw in SRAM. In fact, most of the low-cost Z80 systems you see dotted around these days just have a Z80, a couple of the large-scale in-out devices, and an SRAM chip. But what I'm trying to do here is demonstrate what it was like to design systems like this without the large-scale integration support chips. Partly for fun, but also to really fully explain how the inner workings of these devices work. Even the modern chips tend to use very similar techniques to what we're doing here. It's just not as visible because all the electronics is encapsulated within the ICs. So I put together a discrete video in-out circuit, and that was based on some counters. Had some more comments saying it looks very similar to other machines they've seen. Yes, I did say in the first video that these are common techniques. Normally, though, as I say, it's all hidden within the various large-scale devices. Machines such as the Z80, the Spectrum, this sort of thing. The Spectrum used DRAM, but it had a built-in custom controller chip, and we're not using that. We're doing it all the old-fashioned way, using discrete ICs, and hopefully this will make it far clearer as to how these circuits work. It's nowhere near as complicated as I think a lot of people assume when you see these schematics for vintage computer systems like this. They are, or at least they seem to be, horrendously complex, and they are fairly complicated, but they're also quite easy to understand once you know the basics. They only seem kind of insurmountably complex when you don't know exactly what each part of the system is doing. But once you've built one like this and you fully understand the inner workings, everything starts to become clear, and when you then see an old design, it's much easier to figure out exactly what it's doing, because you can then associate each part of the circuit with the one that you built or one that you worked on before. So we'll start this discussion by having a look at the Z80 timing, and again, this is always worth looking at. This is out of the Zilog Z80 CPU user manual. It's quite a useful document to have a browse through. It's quite interesting, even if you don't want to build a computer. So the instructions for a Z80 are basically in two chunks, or maybe two chunks, maybe just one, but usually it's something that looks like this. So we have the first part, and then we have one of these cycles as the second part. The first part is the instruction fetch, and this is common to all the Z80 instructions, and it has to come first because until the Z80 has fetched the instruction, it doesn't know what the instruction is going to be, so it can't do anything until it's fetched it. So the first thing it does is in the first 4 clock cycles, and this clock is the clock going to the Z80. And in our case, that's the 2.7 megahertz clock that's divided down from the 10.8 megahertz main clock. And that is important. We'll come back to that through this video and explain the reason why we divided the clock down in the first place. So the first 2 phases of this is deemed to be the M1 cycle, by the way. It's the instruction fetch cycle. So the first 2 clock cycles in this are where the Z80 will put the current program counter onto the address bus, and it will fetch the instruction located at that memory address and put it into its internal instruction register. During the next 2 clock cycles, it's actually decoding that instruction, so it can't really do anything external to the processor at that point, And so Zilog took a clever step here, and they built into it the refresh cycle, which occurs over T3 and T4 during the M1 cycle. And this is something we'll make use of in our design to refresh the DRAM. So that's another thing with this design, is that I'm not going to be using SRAM for the main memory. I could do, but that would be far too simple. I'm going to do it the hard way, and we're going to use DRAM. So we will make use of the refresh. Now once the Z80 has loaded the instruction, quite often it will need to do a memory read or memory write. So this is showing both cycles, but normally it's one of these or the other. And these normally take 3 Z80 clock cycles to complete. So the read cycle is the simplest, and it's just going to get some data from memory, and the write cycle slightly more complex, and it's obviously going to write data to memory. Now where it gets complicated for us is that if you wanted to use SRAM as we did in the previous video, you can just hook that up through a very simple decoder, which is what we did for testing, and then you can write data to the SRAM, read it back without any real complication. Where it gets difficult is if you want to use DRAM. So this is the timing for a typical DRAM chip. And as you can see, it's somewhat more complex than an SRAM, but it's not all that difficult to understand once you get used to it. So if you imagine merging all these parts together, it works the same way as an SRAM, that we send it an address, and then if we're reading the data, we then read back the data that the SRAM puts out once we've enabled it, and then the reverse is true when we're writing to it. We put some data onto the data bus, set up the address, strobe the write line, and then the memory saves the data. But with a DRAM it's somewhat more complex, and it's made all the more complex by the fact that if we take a small DRAM chip, maybe 16-pin DRAM chip, which is the package type that we're using, it's a 64K by 1-bit DRAM, and because it's 64K it needs 16 address lines to address all the bits that are inside it. And in a 16-bit package, obviously there aren't enough pins to apply a 16-bit address, because there wouldn't be any pins left over for anything else. So the way that these devices operate is we send it the address that we want in 2 chunks of 8 bits. So we send it 2 8-bit bytes as the address, and we do that in 2 steps. So the first 8 bits is the row address, and the second 8 bits is the column address. If we're doing a read, for example, we'll put the address onto the address bus. We'll send the lower 8 bits to the memory chip. We'll then strobe the row address line, so the RAS line, and then shortly after that we'll change the address and we'll put the column address, which is the upper 8 bits, onto the address bus going to the memory chip, and then we'll strobe the column address, which is the CAS line, and then shortly after that the memory chip will make the data available to us, and then the Z80 can read it. And something similar with the read is that we'll put the lower 8 bits onto the memory address pins. We'll strobe the row address line. That will latch those 8 bits into the memory chip. We'll then put the upper 8 bits onto its memory address pins. We'll lower the column address strobe line, and that will latch the upper 8 bits, and then we'll lower the write enable line, and the data that we put onto the data bus will then be latched into the memory chip. In fact, we're using a slightly different system. Most DRAMs will support what's called early write, and in early write what you do is you lower the address line, the strobe line for the lower address, and then shortly after that, and before you strobe the column address, you will lower the write line. So it's the RAS will go low first, and then the write line, and then you send the upper 8 bits of the address and lower the CAS line. So it's RAS, in this order you go RAS, write, and then the CAS line, and that puts the device into early write mode. The main difference is that if you look at the pinout for these devices, you'll notice that they don't have a chip enable pin. So the output pins are enabled by virtue of the sequence that you send them through the RAS and the CAS lines. So normally if you're doing a standard write cycle or a read cycle, you'll send the lower 8 bits, lower the RAS line, send the upper 8 bits, lower the CAS line, and when you lower the CAS line, the output pin is enabled and it will start outputting data onto the data bus. And that means you have to have a buffer chip between the memory and the CPU data bus, otherwise there'll be contention on the two buses. But when you have early write, the lowering of the CAS line does not put the output pin of the DRAM into action. It stays in its high impedance state. So in early write, the output never changes state, it always stays in high impedance, and that means you can actually connect the input and output line of the memory chip together, and you don't need a buffer between the memory chip and the CPU as long as you adhere to the requirements for the early write. It just saves complexity in the system as long as you design your control logic to ensure you always use early write. If you don't do that, you'll end up with contention on the data bus and you probably damage something. But it's quite a nice feature of these devices, and it does save on complexity for the system, because then of course you don't need to build into the system the control logic for your buffer chip, because there isn't one. Okay, so now we know what the basic timing is we're looking for. We can simplify that, just make a sketch of the required timing, and this is what we end up with. So the clock at the top is not actually the Z80 CPU clock. This is the main clock, the 10.8 megahertz clock, and that gives us about 45 to 50 nanoseconds for each half cycle of that clock. And because we have 50 nanoseconds for each of these half cycles, that gives us the possibility of timing things to the nearest 50 nanoseconds. If we use both rising and falling edges for our control logic, we can control things very accurately. So what we do is we decode the output from the CPU, which is, we did that already in the previous video. We had some simple address decoding. We decoded the memory request and the read and write lines, and we were using that to control the SRAM. The SRAM is no longer connected, but we still use the output of that decoding and memory selection. We don't connect it directly to the memory chip. We instead feed it into another circuit, and that circuit is used to generate this sequence. You can see it all happens fairly quickly. So the read line of the Z80 goes low when the Z80 is carrying out an instruction that results in a memory read. We decode that, and it takes about 10 nanoseconds in our circuit for that to be decoded, and then that is used to lower the RAS line, which is what's used to latch the lower 8 bits of data into the DRAM. The multiplexer we're using in idle state is normally already connecting the lower 8 bits of the address line to the memory chip, so it's already sending the correct data through to the memory chip. So that takes about 15 nanoseconds from the start of the cycle. That's from when the Z80 lowers the read line, and what we have to do then is change the multiplexer to connect the upper 8 bits of address to the memory chip. So we do that about 45 nanoseconds after the falling edge of the read line. That then connects the upper 8 bits to the memory chip. We have to wait a short time to allow the multiplexer to propagate that address through to the memory chip, and a short time for the memory chip itself to respond. We then lower the CAS line. That will latch the upper 8 bits of the address into the memory chip, and then shortly after that the memory chip will output the data from the selected address, and the Z80 can then read that data from the data bus, and then the cycle will end at the end of the T3 part of the cycle. For a read it's something fairly similar. The main difference is that the write line goes low halfway through the T2 cycle rather than the T1 cycle, and that gives us much less time to go through this sequence. But as you can see, this sequence only takes a little over 100 nanoseconds to complete, and in each half cycle of the Z80 clock we actually have 4 times as long as this, so we have several hundred nanoseconds to play with, and that allows plenty of time for the memory chip to respond. In fact, we have around 300 nanoseconds almost of overhead, and we're using 150 nanosecond DRAM, so there's plenty of time for the DRAM to respond. So our task here is to put together a circuit that will generate these signals for us and do so in a timely fashion. And this is where dividing the main clock comes in very useful, because it gives us the ability to time things very accurately. So if we look at the basic circuit I've put together for doing this, and there are many ways you could do this. You could use shift registers, you could use timer ICs if you want, but in a high-speed circuit it's not a particularly good way of doing it. But this is the circuit for our memory decoding and the logic decoding for the memory access, and also our DRAM control circuit. And you can see very straightforward. There is a latch over here of course, but it's very straightforward. It's only 6 ICs, and this is the circuit, at least part of it. So this is the timing we end up with. So the way this works is we have a line coming in that is going low whenever the RAM was being selected. So that was previously the chip enable line going to the SRAM, and that only goes low whenever the system is trying to access that RAM, so it's already been decoded. We've got the refresh line, which we need in order to allow the refresh cycles to work, because of course this logic also has to pass the refresh address and the RAS only line to the DRAM whenever we're going through a refresh cycle, and this has to do both of the memory access and the timing, and also the RAS only refresh. We then have the write line coming in. So this is the write line that was previously going to the SRAM, and that's used in conjunction with the RAS line to provide a memory write signal. So this is a slightly delayed write signal. If you recall, we needed to lower the write signal shortly after the RAS line, and this gate provides enough of a delay to satisfy the requirements of the DRAM, and that means that we can use this combination to put the DRAM into early write mode. We then have a couple of latches here, and they're fed through alternating. Let's get the other diagram back. So on this diagram we had this 10.8 megahertz clock, and to keep this duration fairly short I'm using alternating edges from the clock. You could have of course used the 2 rising edges, but that would take 100 nanoseconds between these steps, and by using alternating edges of the clock we can reduce that to 50 nanoseconds. The DRAM only requires about 30 nanoseconds for that, so we're still well within what the DRAM will accept. And so this is the main 10.8 megahertz clock coming in, and this provides the outgoing multiplex control signals along with the CAS strobe signal, and it sequences this correctly to meet the requirements of the DRAM. Once it's got into this state, the state will persist. The Z80 effectively releases the write line halfway through the T3 cycles. There's still half a Z80 clock cycle before the memory needs to kind of let go of the bus and finish the entire sequence. And as we can see, this the period required for us to unwind this using the clock is only 100 nanoseconds. So 100 nanoseconds after the Z80 releases the write line, we complete this cycle, and because there is about 300 nanoseconds allowed for us to do this, we still have 200 nanoseconds spare, and that means the system is working well within the required parameters, and there's no chance of any overlap or any issues. It does even mean if we want to, we could double the clock speed of the Z80 and we still would have plenty of time to use 150 nanosecond DRAMs. So this works quite well, or at least it does on paper. So what we're going to do now is have a look, and we'll look at the signals. We'll hook up the logic analyzer. I currently only have one DRAM device hooked up, that's this one kind of underneath all these wires down here, but the reason I've only got one hooked up is if I make a mistake with any of this, then it could damage the DRAM, and rather than destroying 8, because I'll need 8 for the 8-bit data we're going to use in this, rather than destroying 8 at once, it would only destroy 1. Hopefully I won't destroy any, but let's see if it actually works. So the first thing to look at is on the scope. I'll do a single capture. This is now running, of course. I'll do a single capture. And what we're looking at here is the yellow line at the top is the 10.8 megahertz clock. So that's this clock going in. It's quite hard to see because obviously with this setup it's not a particularly good looking square wave. It's one of the difficulties in working with breadboards. But on the rising edge of the clock, so remember that we're effectively trying to use the edges in alternating steps, so we'll use one edge and then the other. The first edge controls the RAS line, which is the green line. The purple line is the write line, so you can see that we are effectively generating these two signals. That's the RAS line and the memory write. And we're getting, this is 100 nanoseconds per division we've got this set to, so we're getting about 15 to 20 nanoseconds between these two, which is perfect for what the DRAM wants. 100 nanoseconds after the RAS drops, the blue line is the multiplexer control line. That goes high to switch over the multiplexer, and then shortly after this, it's not shown on here, but shortly after this the CAS line will drop as well, and it's that's done 50 nanoseconds after the multiplexer line. It's actually the next clock cycle, so that will change state shortly after the rising edge at this point, so it would actually change here, and that again gives us all the timing signals we need for the system to work, at least in theory. So nice clean signals, they're looking very well timed, it's consistent, and because we're using an actual clock to time this rather than analog delays or anything else, then it will always be the same, and it will also track up if we decide to change the clock frequency. So what I'll do now is I'll get the logic analyzer started up, and we'll have a look at this and see if we're actually reading and writing the correct data to the DRAM and if it's been retained. So looking at the analyzer screen, I've got this set up for the Z80. Now I'm clocking this analyzer, it's in state mode, I'm clocking it from the clock going into the Z80 rather than the 10.8 megahertz clock, so we can't look at all the individual detail. We'll come back and look at that in a future video, so I will be doing the usual, making a PCB to house this part of the project, and once I've done that and it's a bit more stable and it's not as susceptible to be moved around, I'll do a bit more of an in-depth discussion and demonstration of the various signals. But for now, just bear in mind that we will be kind of skipping over some of the data because the analyzer is only updating every 200 nanoseconds or so, because that's what the clock period is going into the Z80. So I got it set to trigger on an address of 0. We've got the same test code in the ROM as we had in the previous video, so I'll arm the analyzer and it should be triggered when it reaches that address. Okay, and it's been triggered. We can see the instruction it's picked up there is 3E, so if you recall that's the correct one. And if we go through to the point at which it is trying to read the address, which is, if you recall, at address B, so A, B, and the address was 4000. So you can see the data that it's seeing at that address is 7F. Now, because I only have one 1-bit memory chip, I can only connect it to one data line at a time. So what we'll do is we'll run through this 8 times, and at each step I'll move the I've got a jumper that connects the data input and output pin of the DRAM to one of the data lines coming from the Z80, and so each time we run this I will make a note of the data value we're seeing, and then we'll look at that once we've finished all 8 and try and figure out if the DRAM is working. It's going to change the trigger address to save me having to scroll through each time. We'll re-trigger it, and now we're triggering out to address B, save us a bit of time. If we go across, we're seeing 7F. Now notice this time, if you go back and look at the previous video, the address we were seeing was almost 4000, even though the program was supposed to be incrementing the address. And that was, of course, because I didn't have the address lines hooked up, where I do now, and it is doing what it's supposed to. Also notice down at the bottom we're getting the refresh cycles showing in between each of the instructions. So again, that is correct, and if you work out what's down here, that's correct as well, as is the address. So we're getting 2 chunks for the address going through to the DRAM, and then we're getting the value for the actual instruction address, which again is correct. So I'll make a note of this first one. This is on address line on data line 0, so that's 7F. I'm going to move the jumper now onto data line 1, and we'll repeat this. So this time we're getting a value of 7C, so it is at least changing, so that's a promising sign. I'll go through and do the remaining 6. What I'm going to do is move the jumper to each data line in turn, re-trigger the analyzer and make a note of the value that we're seeing. Okay, that's the last of the data lines, and we're seeing a value of 7E there. Okay, so I've made a note of those. It is consistent. I've tried each one a couple of times and we're getting the same value each time. I'll now move the camera down and we'll have a look at the data that we've collected. So to try and get some idea as to whether that system is now working with just the one DRAM hooked up, remember I was in turn hooking it up to each of the individual data lines, starting at data line 0. And this is the value we were trying to write to memory. So only 1 bit is going to be correct for each line. The rest are just whatever was on the floating line, because we were trying to read the line about 50 nanoseconds after the CAS line changed state. More than likely whatever was on that line as seen by the CPU is whatever was there previously, but the line that we actually had connected should have been actively driven to the correct value. So for the first bit, and this is bit 0 on the right and bit 0 at the top, so on the first one we should have a 1, and we do. The next one should be a 0, which is correct. The next one should be a 1, followed by a 0, followed by a 0, followed by another 0, followed by a 1, followed by a 0. And so the value we're getting when we're doing this test is a 1, a 0, a 1, that's the ones I've circled, 0, 0, 1, 0. And if we look, that's exactly the same as the value we were trying to write to memory. So in theory at least, if we'd hooked up all 8 memory chips, we'd be getting exactly the right value. And also you may notice, if you look back at the video, the address was changing as well as we were going through the test. So sometimes it'd be 4000, sometimes 4001, 2, 3, 4, etc. as the address was counting up in the program. And despite that, the value coming back was always correct. So it looks like the multiplexer is correctly sending through the proper address as well. So it's looking quite promising. Just move the camera. So that's where I am with the project at the moment. The decoding and the DRAM control seems to be working. It appears to be able to successfully write to and read from the DRAM. So in the next video, what I will do is I'll hook up the DRAM board I made. So all this really does is allow me to connect up 8 DRAMs exactly the same as this, but without having hundreds of jumper wires going everywhere. So we should be able to do a proper full test on the DRAM, and if that works, I'll write some more comprehensive test routines and we'll do some proper testing on the DRAM. But it's looking promising at the moment. All the timing seems to be correct and the decoding is working. All we'd need to do to add the ability to talk to other devices is modify the memory mapping. It's not going to change the way that the DRAM control works, and so it looks like we're getting fairly close now to having the memory part of our system sorted out, and we should fairly soon be able to hook this up to the video output and start trying to generate some proper information from our system. Still a lot of work to do yet, a lot of design, but as you can see, we're making progress, and hopefully it won't be too much longer before we get a functional Z80. I will come back in future videos and go over these circuits in more detail, or if you're interested, obviously all this will be very detailed in the book I'll be releasing as part of this project, but hopefully you're finding this interesting, and we should end up with quite an interesting project that really shows the inner workings of this type of system.